And then I'm going to let much smarter people give you more information about some of the cool research that we're doing, and really is some of their amazing work in trying to sort of better understand brain injury really at the tissue level. So will the arrows work, or do I need to use it? Okay. So just a quick background, if you didn't know, the US Soccer Federation in 2016, in response to whatever, of course, like lawyers been getting sued, the class action lawsuit changed soccer heading rules for youth soccer such that in 11U programs and younger, they're not allowed to head the ball at all now. And there's limited heading for slightly older groups, 12U and 13U, where no more than 30 minutes of heading per week and no more than 15 to 20 headers per player per week, but there were no restrictions in games. And I think this was largely reactionary. I don't know that there's not a whole lot of data to support like how concerned should we be about the effects of youth soccer heading. But legal things like this drive change, whether you think they're data driven or not, as we all are all aware in the sports world. But what is the purpose of heading? It's right an integral part of the game of soccer. Use it to pass, shoot, clear the ball. It can be direct or indirect, flipping the ball off your head. It occurs in all different situations: corner kicks, punts, goal kicks, free kicks, throw-ins, other types of kicks, crosses to an attacking player. It's a learned skill. And we can debate, probably with any of the coaches in the room, if there are some, like, what is proper heading. And I learned from Drew Watson, who's one of our other team physicians, who's also a youth soccer coach. There's not really like a standard curriculum. There's not like an accepted, like here's how you head the ball. I think every soccer coach has probably the same sort of general approach, but there's not, sort of a clear, like, here's how you teach soccer heading, like there is, I think, more in the like body checking the ball, exactly. But in general, right, you want to have your eyes open. Closing your eyes, probably not a good strategy. You want to generate power with your body. You don't want to be passively like the ball is hitting you. You're passive. The ball is attacking you rather than you attacking the ball. Contact, here on the front of the forehead, not, bouncing it up all other parts of your head that you didn't intend to, and then follow through again. It's an intentional act and something to drive the ball in a certain direction. Just some quick data on youth soccer heading, just about like the number of soccer headings that might occur in like a youth game, to give you like some idea of like how common is heading in youth soccer. So this was a European study. They actually studied like almost 500 soccer matches, one match per team, and all these different age groups, male and female, to see, well, how many times you've actually hit the ball. So the black box is like they didn't head the ball at all. This one is only 1 to 2 times, 3 to 4, 5 to 9, and then there was only kind of one, some of these older groups where they actually had it more than 10 times. But almost 80% of kids in this study didn't like head the ball at all, or it was like only 1 to 2 times in the entire game. But there were a few kids, like this under 16 male group, where there were a couple of kids who like headed the ball quite a bit. And we all like know that, right? There, some of that's positional, some of that style of play. Some players may not literally touch the ball at all with their head, and then other players, it's 10, 15, however many, times a game. But overall, I think I can legitimately argue that like they don't hit the ball that much in youth soccer, even at the like U16 level. Here's the only study I could find that really directly compared youth soccer and youth football, right? Because so much of the research has been focused on football, which is one of the reasons we are working in a different sport, because like the world of football and concussion and head injury is like pretty crowded. So if we compare soccer, U12, U14, so kind of similar age, 11 to 13-year-olds, The soccer season was a much longer soccer season, so it was 9 months. It totaled 60 games and practices. There was a total of 132 headers per player over the course of that 9 months. The max was 450, right? So then there are some kids who are heading it quite a bit. A lot of the kids are not heading it much at all. But it, it averaged out to less than 2 headers per player per game, and the max was like 15. So there were some players who were in that 15. So let's just compare that to football. It was a much shorter season, only 3 months, 27 practices, 9 games. There was a total of 252 head impacts per player, up to a max of 880 over the course of the season. So on average, 12 head impacts per player per game, and maybe a max of 50. So I would argue, right, we should probably be more concerned about head impact exposure in youth football, at least just looking at this one, study that we can kind of directly compare age to age. But should we be worried about repetitive and cumulative head impact in young athletes? Well, yeah, of course. Like, I believe in no head impact is good head impact, right? And particularly for young developing brains. In soccer, due to purposeful heading, which involves repetitive head impact, I don't know, maybe. I think we obviously need more study, which is why we're working in this area. I would argue that heading is really not that prevalent at the younger age levels, but with increasing age and level, of the sport, level of play, then obviously the number of headers is going to increase. So, like, what about lifetime number of headers? Even for our collegiate athletes, if you play for college, like, how many times have you headed the ball over the course of your lifetime? And is that a concern? I didn't show you some of the head impact magnitude data because Dr. Tripathi and Dr. Carlson will review some of what we've been studying. But overall, it's relatively low, but not zero. Right? It increases with age and level of play, probably correlating with ball velocity, right? The bigger the kid, the harder they can strike the ball, then the faster the ball, the higher the forces and the ball strikes the head. So again, like, what about lifetime exposure? And are there certain types of forces that are more injurious, like kind of a more straight on linear versus kind of a more rotational force? So really, like, what are the consequences of like cumulative impact exposure? And so what can modeling tell us about the risk of injury or the strain to the brain tissue in various soccer heading scenarios? And this is where I'm going to invite people who are like way smarter than me to talk with you about their super cool work, developing these force strain models and brain injury probability maps to really sort of get an idea of like how concerned should we be about this causing injury truly at like the cellular axonal level. And then, now what do I do? This is our group that we're working with. This is a part of a bigger, kind of larger study. We're going to talk with you about the information from the header study. I forgot I had more slides. Dr. Tripathi and Carlson are going to share with you some of the data from this sort of header study where we took kind of a younger-ish group, 12 to 13-year-olds, an older-ish group, 16 to 18. We shot soccer balls at their head with the jug machines at relatively low speeds. Okay, so I looked at what was in the literature and we took like 50% or less of like the speeds reported in the literature. But we tried to simulate different heading scenarios, a throw in, kind of a shot, like a cross shot into the goal, and then like a clear. And so we had them do it once, then we gave them a little training session on like how we properly had the ball, and then we had them do it again, and we also changed the pressure of the ball to see how that matters. So that's sort of our general testing scenario. So they're gonna share, and then they all had MRI scans, so we can actually look at their brain anatomy, and then pair that with head impact data because they were all wearing this headband with the sensor on the back, so we can measure the head impact forces every time they did one of these heading scenarios. So that's this header study, and that's the data that Dr. Tripathi and Dr. Carlson are going to share with you. Okay. Now,
should I share?
Yeah.
I think you can go ahead. Yeah. All right. So as Anu gets those slides up, I just want to say a few words. Can you guys hear me okay in the room?
Yep.
Okay, awesome. So a few words about our group. So first of all, we're really excited to work with Dr. Brooks and the team at the University of Wisconsin on this project. And so the goal of our group is to develop computational models that allow us to predict the risk of concussive injury for a given head impact. And so we're looking at concussive injury, but also we can look at subconcussive impacts to the head and the brain deformation that results from those types of impacts, which is the case in the soccer header study. So Anu, we can go on to the next slide here. So what I'm going to do right now is just give you a big overview picture of what we do as far as our workflow is concerned, and then I'll hand things over to Dr. Tripathi, which she'll go through some of the specifics of this study and share with you some of the results that she got so far. So like Dr. Brooks said, we have these wearable sensor systems. So we're currently using a headband with a blue trident sensor. So this particular sensor has linear accelerometers that allow you to measure the linear motion of the head, as well as gyroscopes that allow you to measure the rotational motion of the head. So for a given head impact, then we can get the full head kinematics. So we can get the full motion of the head in space. And then we take that sensor data and we use that as an input into our computational models. So we're using these finite element head models. And so what we can do is apply that as a boundary condition and actually simulate that particular head impact. Now, one of the unique things about our finite element models is that instead of using a generic head model, like Dr. Brooks says, we're actually using subject-specific medical imaging data to actually create a subject-specific model. So we're taking magnetic resonance imaging data, diffusion tensor imaging data from each subject in our study. And then from that, we use some software in order to create a 3D head geometry. And so we can segment out different functional regions of the brain, different anatomical structures so that it's specific to that particular subject. And then we can go ahead and simulate that head impact event. And then from there, we can assess the tissue strains and strain rates in the brain, which Anu will talk more about that. But basically, we're looking at the brain deformation response, and then we correlate that to known thresholds of injury from some other studies. And so we can predict the risk of injury for that particular event. All right, so now I'll hand things off to Dr. Tripathi, and she'll talk more about the specifics of this particular study.
All righty. So I hope everybody can hear me fine. So hi, everyone. I'm Anu. And today I'm going to talk about the soccer header project. So this entire project is based on the concerns regarding the long-term effects of repeated soccer header drills based on a lot of previous studies. So for example, in this study, they say that King-Devick test is one of common tests to test actual injured concussed player if they are safe to go back on field or not. So they used this test on players that underwent repeated soccer drills using a softball, a hardball, and a control group. And this is like pre and post reading. And what they concluded was that even though none of them actually suffered an actual concussion, they were still not able to pass that test. So that is like a clear indication of a subconcussive effect. And then there are similar studies on motor tests and biomarkers, but all of them are contradicting each other. Like some find very significant correlation and some find that there is no correlation. And on top of that, there are some sex and age-based differences. So for example, women report higher number of concussions, whereas US Soccer Federation imposed like an age-based restriction, but all of those are not based on a scientific understanding. And that's where our study comes into that we are trying to understand what is happening actually in a header and what is the brain response difference between different individuals. And if there is a significant difference in the functional region that is affecting different age group and sex group. So before I deep dive into this particular project, I want to first explain what can we do using finite element modeling. So once we have, let's start here. Once we have a subject-specific finite element model, we can apply boundary conditions and simulate this whole soccer header. And from there, we can obtain different measures. For example, in this plot, I'm showing how strain and strain rates are changing with time. So what is strain and what is strain rate and why they are important? Why are we looking at those things? So strain is a measure of deformation, material deformation. So for specifically, how is the change of length with respect to the original length? And then strain rate is how fast is the strain changing? And why is this important? This is important because experimentally we have correlated, not we, like scientific community in general, have correlated that with injury. So if this is the axis starting from 0 strain and strain rate to whatever, increasing. So in college football, computational studies have estimated strain to reach up to like 8%. In mixed martial arts, it can reach up to 9 or 10%. In NASCAR, it can reach up to 12%. And experimentally, many studies have shown like if you reach from 15 to 20%, you start experiencing functional damage to neurons. And beyond that, there is some structural damage where if you have this neuron and you apply strain, it starts developing bulb and eventually disintegrates. So that's why strain and strain rates are important. So with that information and our objective, we design our study. So we have players of different age and sex groups. And while heading the ball, they're wearing these headband mounted sensors that can obtain the head motion kinematics. And this will serve as the boundary condition for our simulation. So we take this, we take subject-specific MRI scans, develop our subject-specific models, and then we can obtain those strain and strain rate maps in the entire brain. And then we can also do more trend analysis and get these different trends of how the maximum strain and strain rate in the entire brain is changing with time. And we can repeat this process for different individuals and then compare how the response is changing. So in this study, there are like different layers where the individual differences might be introduced. First layer is this head kinematics. If two people are heading balls, the kinematics of their head motion might be different. And another place where differences can be introduced is the head geometry. So with that in mind, we here today I can show you some of our preliminary analysis on two different subjects, two different topics. So first topic is effect of heading techniques. In this, what I do is I have different headers. One is a good header and one is poor header technique, but I keep the head model to be the same. And in the second study, I will look into the effect of individual anatomical differences where I keep the boundary condition, the header to be the same, but I will look at different head models. So moving on to the first study, which is the effect of heading techniques. So before, let me also describe, add on to what Professor Brooks was explaining before, what we are trying to do here, like our experimental design. So first we try to simulate the headers, what a middle school soccer player would be experiencing. So we have three kinds of headers. One is throw in, where a person is standing like 5 to 6 meters and throwing a ball. It looks like this. The second is a goal kick. In this, we have a jugs machine throwing a ball from like 18 yards and 20 miles per hour speed. And it looks like this. So similar to throw in, but much higher intensity. And in a corner cake, you have to direct the ball to a different direction like this. And in all these three, the person is wearing sensors, and these sensors can give you rotational kinematics as well as translation kinematics. So here I am showing rotational kinematics. So each of these peaks correspond to a header. But today I will just focus on the throw ins to begin with. So next thing is, in our study, we identify a good player and a not so good player. A good player is like by the book. So you take the stance, you tense your muscles, you hit the ball where it's supposed to hit, you direct it where it's supposed to go. So for these are like good throw-ins and these are poor throw-ins. First row is the video, second row is the translation kinematics of the head, and third row is the rotation kinematics of the head. So we see here, this is a throw-in header of a good type, good technique, and similar to this, this is a second good throw-in task. And a poor throw-in task is somewhere you are not in control of the header as much as a player would be. And so you're hitting the ball more passively as opposed to in a good throw-in task, which is more active. So in terms of kinematics, what we see here is that in poor throw-in tasks, your rotational velocity is slightly higher or much higher than your good throw-in tasks. So we take a good header and simulate it. So these are the loading conditions, and I just apply that on a head model. And this is the result of the simulation. So on the right, we have these strain contour plots. And what we see here is how the strain goes from the surface of the brain towards the center. So I want to take like a minute to explain what is happening in a soccer header. So when the ball hits the head, your skull is rigid enough that it shields the brain tissue from the direct force. But because your neck can move and you have finite mass, your skull starts to rotate, and that starts the shearing of the brain tissue. So that's why the strain starts to appear on the surface of the brain, and then it starts to propagate inside. And then it mostly is concentrated on the surface because as it propagates inside, it loses some energy, but it's also concentrated somewhere in the center near the ventricles as well. So these are the results for all the 4 cases. So these are the 2 good throw-in tasks. Starts from the outside, goes propagates inside. And this is another good throw-in task. So similar distribution, but slightly lower intensity. So this is 0.08, this is 0.06. And here is like a poor throw-in task. So similar distribution of strain, but slightly higher intensity. And similar is the second poor throw-in task, where higher intensity, but similar distribution. So next, what I also did is, so first I showed you like a global description of the strain and strain rates. Here I'm showing like region specific results. So this is the strain and this is the strain rate plot. I'm comparing the good headers versus bad headers strains in a particular region. So for example, gray matter, white matter, thalamus, hippocampus, amygdala, brainstem, corpus callosum, and cerebellum. And in all of these, what I see in general is that a poor technique will yield you a higher strain, and that is can be correlated with the higher skull rotation velocities that we measure using sensors. And second thing is also that we see much higher strains in brainstem corpus callosum. But again, another thing to keep in mind is these are just two headers. These are not very statistically significant, but this is what we get from a analysis. And then moving on to the second study, which is the effect of individual head differences. Here, I keep the header to be the same, but I change the head models. So we take a throw-in header, and we have this head kinematics. Then we apply it to 4 different individual heads. So on this slide, instead of showing you the video, I'm showing the snapshot of the strain contour plots. So each row is separate individual, and each column is different timestamps. So starting from 10 milliseconds all the way to 50 milliseconds. So here we see similar thing that we saw in our previous study, that the strain starts to occur on the surface of the brain and then starts to propagate in. But as it propagates in, it starts losing the magnitude because of the energy dissipation. But it also starts to concentrate near the ventricles as well as the falx and tentorium, where all these deep brain structures are. And then if we compare all these strain plots between different individuals, we see a similar pattern in general, that the higher strains are concentrated on the surface of the gray matter. But we also can see some differences, like here the strains are concentrated near the front of the brain, but here it's concentrated near the back of the brain. And we can go ahead and do a lot of in-depth analyses, but today I'm just going to show more of a global comparison. So global in the sense the entire brain rather than region specific. So in this plot here, this is the maximum principal strain in the entire brain, and how that is changing with time for different subjects. So here, all these curves are for 4 different subjects. And the similar plot on the right is the maximum principal strain rate and how that is changing with time. And what we see here is that there is considerable variability. So as much as 16% strain variability across different subjects, indicating that subject-specific modeling can be important and the way to go. So for today, and these are the results. And our next step is, so till today, I just showed till this point that we have subject-specific models, we apply sensor data, and we can get strain distributions for different headers and for different individuals. What we need to do from moving on is also get a cumulative damage after multiple headers. So for repeated header drills, how things are being cumulated. And another thing is to look into the region-specific strain and strain rate so that we can then go back and correlate it to different age and sex groups. And lastly, I would like to acknowledge my friends, all the postdocs, Sashan, Yahweh. So this is Yahweh, this is Sashan, Juliana, and all the undergrads. They helped with developing the head models, and our collaborators from Panther team and PTVI team. So thank you.
So our next step with this study, so also we just took 10 kids in each of these age groups, 10 younger boys, 10 younger girls, 10 older girls, 10 older boys, and we did these heading sessions this past year. And then our goal for this coming year is to actually have certain club teams in the area agree to participate for a whole season, have them wear instrumented headbands and actually measure like real time soccer. But right, this was like not in the lab, but it was in a controlled, field condition. And so how much does that lose? What actually happens, soccer practice in the game. So we're gonna find out and have them wear these instrumented headbands, measure all the head impacts that occur during their practices and then all their games, and then kind of look at things and do an MRI for the season or after the season, do lots of other sort of cognitive measures, some of the other things that we would follow, balance, and see, how things sort of change or what is there sort of concern about accumulation of injury, over time. So that's kind of the ultimate goal this next year. COVID obviously will put us on pause for about a year, but hopefully we'll be on track this year to do this season. So questions, discussion?
At the beginning, you said that a lot of you soccer doesn't have a lot of plan for everyone. Is there anything from also that you hope to
Ideally, yes, we asked Dr. Watson about that, but part of the issue in soccer is it's like so fragmented, like there's so many different groups that have their fingers in the youth soccer pot, and so getting agreement or consensus, I don't know, unless they were able to agree on like there is a universal coaching certification, like you could be in whatever different organizations or clubs, but everyone has to have this same certification. It's very different than USA hockey. Hockey world as a team position, and as mainly the parent though, in USA hockey, it's just like it kind of encompasses everything. Like, there's not much that happens on the level that's outside of USA hockey. And so USA hockey completely, controlled mostly, your required training for your coach, concussion, safe sport, how you teach hockey, body checking. And so there can be very consistent. And US soccer is not like that at all, is what he tells me. But, so I think it's a great thought, but I don't know that it can happen in practice because the soccer world is so fragmented. But maybe we'll find, obviously, we'll go back to it, but like our hope is to find things that are modifiable, right? Like, does ball pressure matter? Does the air temperature matter? Cold winds versus warm weather, technique. There's certain clear things about technique that matter, and I think you could argue say we should teach the skill like football and like right heads up and head out and play it. Those kind of things. So.
There's been obviously invited to on football or soccer with them studying periodically.
No, you actually did that study with in the blind a couple of years ago, and like 2,000-ish kids in that study, and even with that number of subjects, you couldn't show any kind of effective effect of soccer year. Now we had to use a bunch of different headbands. We were made to do that for higher than using as long as it was like invest, but always like a little bit, but overall we didn't find a huge difference, at least in prevention of concussion, right? So prevention of concussion injury, which is different than like the concussive like repetitive. There was the suggestion that there might be one grant that others. I don't think we'll have the numbers to look at that, but maybe in a future study. Maybe I just don't expect as well as we do the concussion, but maybe it does matter in terms of like repetitive, dissipating repetitive. The rebuttal to that is always like that we're on and things how people play. So we'll be videoing all of the practices and things that we can to try and look at some of them, like we will get some qualitative subjective information. Does it change their approach to the game if they have, equipment on that they perceive makes them safe, increase compensation, might be more aggressive, change your style for a negative way. Because they're more effective. Just said here, the compression follows the.
I have a question for Dr. Tripathi. Can you hear me?
Yes.
Okay. I don't know if this is more of a question or a comment, but I was thinking about one of the things that you had said, good form versus poor form. And you're I don't know if you had mentioned this specifically, but you're planted, you're following through, as opposed to poor form, it's not as a controlled header. And I'm just thinking about, I myself in the product, like I have had concussions from soccer, from heading the ball, and I feel like most of them happen while jumping in the air. And I think so many times you're jumping in the air. I don't know if there's anything, if that's something that you looked at or anything like that, because I just think of like how many times you jump up and then you get bobbed around and your form becomes poor just by due to nature of hitting people. But it's just something I'm thinking about because I think so often I'm not planted when I was heading. I don't know, that's just more of a comment, I think, and I don't know if your work showed anything in that regard.
So thank you for that. I was not aware of that. And also right now, this is very qualitative, categorizing a throw into any header task as good versus poor. So as many feedback as we can get is great. So thank you.
Yeah, I mean, we debated about whether we should like make like a scoring criteria for like, evaluating header. That would be, there's nothing validated in the literature. I'm sure if we like gave it to all the soccer coaches, they're all like say something different, so I just, it is very, but I think we all understand the concept that we're getting at, which is, eyes open, head at the target, you're purposefully sending the ball somewhere as opposed to like, some of the younger kids, the videos that we could show, it's like, turning away from the ball, it's not at all an active thing, but that makes some difference. But again, but I think you make a good point, like this very controlled setting, remember the videos, like everyone's planning on the ground, if you didn't have them jump the time heading. And I would agree, a lot of like game scenario headers are going to be, I would say, aerial challenges is kind of the, where two players are competing for the ball. And sometimes the issue isn't right, it's not the impact from the head to the ball, it's the impact of head to head or elbow to head, overhead, or ground, you hit the ground, hit the ground. So I think it's going to be really interesting to see what we find when we do the season study, like real world. And I think you make a really good point. It's maybe that unexpected contact that changes things. And we certainly know from concussion work, right? That like that unexpected, something, right? ACL is the same thing, right? That unexpected perturbation. And so that may really change the course of the brain experiences. And you're right, I think that's much more likely if you're in the air when you don't have really as much control over things like that.
I'm too, I was interested in the model here with the different things. And it looks like the female 9-year-old is lower on the string than the.
Yeah, I don't know, if Nuke, you can go back to that slide.
And maybe
Um,
it's a negligible difference. But, you know, a lot of the, or at least some talking about that, you know, especially and young people in general, or next thing, maybe that ability to stabilize themselves, you know, you can't anticipate that it's not too much. I just thought that was.
So, if that is a question for me, I am not able to clearly hear it.
Oh, I guess it's more than more of a comment or wondering why it was a lower, it seems to go against what we thought about before.
She's asking about it looked like the female 9-year-old
Uh-huh.
strain was like lower less, which is like not what you would expect.
Yes,
Just in
that's
general,
that is true, and that was because our 18-year-old female. So this, are you talking about the male 17 years versus 9 female? So that is true, but the thing is, like, there is so much variability within each group that we really need to do much higher number of analyses. Like, we need to have at least tens of different heads models, because like the 17-year-old male head size was very small for a 17-year-old male, and it was actually smaller than this 9-year-old female. So not very representative at this point, and that's why we need to do a statistically significant number of studies, head models as well as headers. So that's why we have not obtained a good anatomical factor, because it's just one subject each, while we need to do like 20 subjects in each group.
But I would agree, it's like not what you would expect younger kids. But we after we got partly through the soccer heading sessions, we realized we didn't ask, as we were just like talking to parents on the sideline while the kids were like doing the session about which club are you from, like, you know, kids are excited to do this, they were a little nervous about doing it, like how much do they have in practice, like that's that. So we like went back and surveyed the parents about, you know, what was their childhood experience, like did their coaches actually actively teach it in soccer practice, how many years of experience have they had with it, were they fearful of heading to try and then see like how does that correlate, because maybe there's some youth headers who are pretty good at this game because they've actually been coached well and they've been doing it, and then, you know, there could also be high school kids who are terrible at heading, you know, or, you know, the opposite. So I think it'll be important that we get all that same information for the student study, but also measuring head circumference, neck circumference, and then measure neck strength, just sort of general balance, performance, some of those other things that also might, that we would presume would be less good in younger kids and some of the reasons why.
I read a little bit, like showing in the study for the reduction effect.
That I recall, and that's like in our study design, it was kind of the last second, like, oh, let's just like throw a little like coaching session in there in between the two, like, you know, and to see what, you know, that it making difference, but not on a large scale, but I.
So like,
Yeah.
what 60 program,
Yeah,
like
no,
something that's actually
nothing.
kind of like
Zero.
one,
We'll do it. Here, you write it up and find the money, we'll do it.
really interesting is the three different types that growing the one within the was there differences in strength among the two types of patterns?
Yeah, I think there will be. Dr. Tripathi, he's asking about, obviously, you were showing data from the throw-in, but he's asking about, what are you seeing with the strain rate for like the clear or like the cross scenarios, which we would assume we would see higher strains.
Yes, that is true. So right now I have only shown the throw ends, but we do expect, because wait, my computer is very slow in going to that slide. So yeah, this is the rotational velocity. These two are the throw-in headers, and these two are goal kicks, and then these are corner kicks. And as we can see, like as we go from throw-ins to goal kick and goal kicks to corner kicks, our intensity increases. So I would expect the strain and strain rates to increase accordingly. But I still have to run all those simulations to confirm that.
Anybody recognize whose head that is? No. He was nice enough, but yeah, test that. And the jugs machine at its highest setting can so of course for giggles, Mac and I were out on the turf fields by the lake shore there, and let's crank it up and high setting, and like no one else is out here, let's see how far it can shoot the ball and it landed. So but I don't know that many soccer teams use this. Do we have anything? Yeah. So, but so they use in most of the research studies to try and give a consistent bit. But we, in terms of like the strain and the strain rates, I think what we're going to find is going to be a lot less in this controlled setting than what we find in real practices and games, because we did not want to hurt we were signing up for a study. We had it be, like I said, 50% less of the miles per hour that's been like reported in the literature. We did go over to the softball training facility. They were nice enough to let us use their radar guns, so we could actually like clock the ball and make sure we were not above like the threshold equal value. But my guess in real-time play, the ball's coming in a lot. No, there was some time. I mean, usually, Dr. Carlson, you might be able to, or Dr. Tripathi, on average, how much time was there between the heading session and when they got their MRI?
I don't know.
Yeah, I'm not sure exactly.
Couple weeks, maybe. Not
Yeah, perhaps, yeah.
for that. We just wanted to get it done, so we tried to give ourselves a pretty large, window. But also for the season study, we'll have to try and get them in right a certain time frame. They can't have their MRI after they've already started the season, but no, it wasn't necessarily like right after, right before the heading session. It might have been, but not necessarily.
Here's the talk to the multiple events across, pull the data from how are you handling?
Well, we're still trying to figure that out. We're for the season study, because of those reasons like that, so cannot follow like 3,000 kids. So we're gonna try and pick like, a team or two, in the young male and young female, a team or two in the older male, older female. Hopefully get the majority of them to agree. So at least having 100 plus sensors, and then do some like coaching of coaches and parents and try and, you know, watch them pay some of the team staff to try and help with some of their, like, making sure they're, you know, take them out, charge them up, put them back in, and then because we will not have enough research staff to be at literally every practice. And every practice, we're gonna hope that maybe we can have research staff member at every game, right? Because I think that's truly gonna be the highest yield data. But it's gonna be a challenge.
Well, special thanks to you three.
Yeah.
Much appreciated.
Thanks, Rika and Anil.
Thank you both so much. Thank you.
Yeah,
Thank
absolutely.
you for having us. You can stop share.